Today we are going to be covering multiple linear regression, and now this is not going to take too long because it's very similar to linear regressions. The main difference is now that there are multiple independent variables, and if you ever begin to or you have read research studies, you'll probably notice that a simple linear regression, so just one independent variable, is not often used. Multiple regressions or some form of multiple regression is going to be a lot more common. So the purpose of the multiple regression is to determine an equation for some dependent variable in terms of two or more independent variables. Now this would be the equation for a linear regression where, again, we have the slope, we have the coefficient, and we have the actual variable. So in this case, in a multiple regression, the only thing that's changing is that we're just adding in more variables. So let's take an example. If we had a question, we want to know what factors influence strength. So if we were looking at the force that somebody can produce, is there going to be more than one factor that influences strength? So yes, of course there's going to be more than one factor that would influence strength. We could say age, fat-free weight, height, body weight, BMI, percent body fat, and a bunch of other examples. So all of these factors work together to influence strength. And if you were running a research study or doing an experiment, it wouldn't make sense to only use one of the factors to actually predict strength. So use multiple regression to determine which factors significantly predict some outcome and what the strength of the factors individual predictions are. So how much does something contribute to the actual prediction of the dependent variable? So this is in your book, and I'm recommending that you read I believe it's chapter 8 on multiple regression. But let's say that we have our dependent variable, and that's isokinetic torque. So let's just think of how much force somebody can produce. And let's say we have 24 participants right here. In the other columns, we have the subject number, age, fat-free weight, height, weight, body mass index, and then also percent fat. So let's say this is our data. So again, these are independent variables, everything other than isokinetic torque. So what we could do first is we want to actually examine the data. So we could tabulate it. We'll do that. It's not really going to make as much sense as if we did actually summarize. So why don't we do this? If you have the PowerPoint and you want to practice it, this should just work for you as well. So if we just did this, that's not giving us too great of information just because we wouldn't expect a lot of people would be within a certain frequency or anything like that. But we can see just the range. Everyone's going to be a 1. So in this case, BMI, we only had an example of 2 where it's 22.25. So probably what's going to be a better command is if I just swap out that tab command. Let's summarize. And then that's going to be better. So now we can actually look at things like ranges. We can look at mean, median, standard deviation. So we're just getting an idea right now of our data. Okay. So now that we just have an idea of what our data looks like, we want to make sure that there's not more than one independent variable. Make sure that there's more than one independent variable, which in our case there is. And we want to make sure our multiple independent variables aren't too highly correlated. So for example, over 0.8. The reason for that is we don't want our independent variables basically to be explaining each other. So let's just see if we can get a good example right here, and you might see that later. So if we had a variable such as BMI and then also weight, we might say that weight is explaining 90% of the variance in actual BMI. So in this case, adding these two to a prediction equation would basically just be redundant. So we'd want to make sure that they're not too highly correlated. And then, so this is where we'll begin. But we want to also determine if our overall model is significant, and we want to determine they explain variance of behavior and determine significances of individual predictors. So let's do a correlation matrix first with all of our variables. So we can just swap this out with PW core and sig, and there's our correlation matrix. So again, just really focus on this. This is our correlation coefficient. This is our p-value. This tells us if it's significant. P-value tells us if it's significant or not. And this tells us the strength and the direction of the correlation. Okay? Let's go back to the slideshow. So this is just what we're seeing right here. So we want to take a look at this and examine the data. So this was what we had on Stata. So we might want to look at what variable is the most strongly related to torque. So we're just saying the amount of force that the person can produce. So let's look in first and see if these are all significant. And in this case, they are all significant. Everything except for fat percentage, which logically would make sense, is highly significant. This is also highly significant, but then if you look at the correlation coefficient, this is the lowest one that we have with a 0.48. Everything else is in the 0.87, high 0.7s, 0.8, and not even 0.9. So if we look at this, we can see that an individual's weight has the strongest relationship with the amount of force that they can actually produce. So now let's run a regression. So you've already done this one before. We'll run a regression with just body weight. So let's go regress, and we want to regress torque, and we want to regress that on the person's weight. So let's see what that looks like. So this is our output, and I'll go back to the PowerPoint to cover it. So right here we can see that 85 or almost 86% of the variance in force is explained by the individual's body weight. So and it's also significant because we see that is 0.000, so it's highly significant. And again, we can see that right here as well. So the model is significant, then also the variable is significant. So what can we tell by this? We can say that for every 1 unit increase in an individual's weight, we would expect force production to go up by 2.17, I believe is Newton meters. So by that many units. Okay, so this is something that we've already done. It's just this part is just a linear regression, so nothing is too new right now. So this is exactly what we're saying is for every 1 kilogram increase in body weight, we would expect torque to be 2.17 Newton meters higher. And we can say that body weight accounts for 86% of the variance in torque production. So what other variables will increase the explained variance? So let's try to add in age. Okay, so let's do that and see what happens. So if you want to make this easy on yourself, just click on that again and add in age. All right, so we want to know, is this significant? So what we would see here is that yes, it's significant. Almost 92% of the variance in torque is explained by a person's weight and also their age. I didn't add beta to the end of this, but that's okay. If you're ever looking at confidence intervals, which I won't be necessarily testing you or anything like that, but if there's ever non-zero values, that also just means it's significant. So right here we'd see that age is a significant predictor of torque, and we'll go into what that coefficient means as well. And what you also might notice is that this number changed, and I'll explain why. Okay, so now age is added into the equation. Again, almost 92% of the variance in torque production is explained by these two variables. So by adding age to the prediction equation, we have explained another 6% of the variance. The results were statistically significant. So the slope coefficient for age tells us if we hold age constant, torque should increase 1.45 Newton meters for every 1.0 kilograms increase in body weight. So what I mean by that is we're holding the other variables constant. So in this case, this was the only variable that we considered. But now when we hold age constant, we would expect that for every 1 unit increase in kilogram of weight, we'd have a 1.45 increase in force produced, okay? So again, now we're holding age constant. We would do the same exact thing, and I asked this in the next part, is if you held weight constant, what would you expect for a 1 unit increase in age, so another year? Well, you would expect the person to increase their torque, the force that they're producing, by 7.6 Newton meters. So what if we added anything else? So let's say we added fat-free weight. Let's go ahead and do that. And we'll just add this right here, fat-free weight. And now if you look at this, the only thing that's significant is age. And so the reason behind that is because I think if we go back to our correlation table, let's look at the relationship between fat-free weight and actual weight. It's 0.98. So they're basically saying the same exact thing. So it's kind of redundant to add this, to add that fat-free weight into the equation. And it's not a good idea to do that, because then if we look at this, it looks like neither weight or fat-free weight is significant, which probably isn't the case. So this isn't adding anything else to the model. If we look at this model, it's explaining about 92% of the variance in the force that the person can produce. But if we did the same exact thing where we did just weight and age, nothing's, it's 0.9186. This one's 0.9198. So it's not explaining anything else. So this, adding this variable to the equation isn't going to be useful. For your own practice, you could still do, you could regress that. We could take out weight, and we could see what happens. So in this case, once we took out weight and we just added in fat-free weight, which you can think of as muscle, then yeah, this is significant. So basically, in this case, we're not really adding anything new to the model. The explained variance is barely going up, and it's not significant either. So the multiple regression, again, it's very similar to the linear regression. We're just adding in more variables, and that's when you have to start paying attention to what actually changes for the coefficients. So again, if we just looked at a single variable right here, we would see that weight, so for every 1 kilogram increase in weight, force would go up 2.17 Newton meters. But again, if we actually start factoring other things like age, we can see that that's going to be a little bit different. So now this value actually goes down. And then also just make note that if you add extra things to the equation that aren't useful, then that's going to make some things that are significant insignificant.